Hi guys, welcome back to another video of Center of Circle. I am Saifan, one of the academic members of Center of Circle, and today we'll be looking at a past Physics Olympiad problem. It's from the national round of BdPHO 2022 and it's from category A. So basically for students of class 6 and 7, and it's a quite interesting problem, and I gave that I sat for that question when I was in class 6, and that was really interesting question, and I hope all of you find it interesting. So let's go straight into it. Right, here we go. So it's the second question of the National Physics Olympiad 2022, and it's quite an interesting one. So I will be showing you all how you can solve all of this, and I hope it will be very interesting. So sometimes they will give you the formulas and you can work on it, but as I said, you sometimes have to know some of these concepts in advance, because in some of the problems they will ask you detailed things, like you need to know about this topic earlier on. So because I didn't know about this topic at that time, I couldn't solve one of these questions, but as I know now, I can obviously show you how to solve these questions. Right, so let's read the question. So it starts off by saying, thermal radiation is one of the main processes of heat transfer. A famous law related to thermal radiation is the Stefan-Boltzmann law, which states that in the ideal case, the power, energy per unit time P radiated by an object with surface area A and temperature T is P equals to A sigma T to the power of 4, where sigma is something. An application of this law commonly seen in our everyday lives is the infrared thermometer. Infrared thermometer measures the power radiated by a small area of our body and then calculates the temperature using the Stefan-Boltzmann's law. An infrared thermometer is pointed at Siam's forehead. The thermometer receives power, and from an area A, what is Siam's temperature in degrees Celsius? Okay, so what do you understand is very important. So I hope all of you know about thermal radiation. If not, let me try to explain what it is. Basically, it's a process of heat transfer which doesn't need a medium. So like, it's not necessary there needs to be a medium. It can travel through anything. Basically the heat we get from the sun is a form of thermal radiation, because we get the heat from the sun, like the process in, like the medium through which the heat travels from sun to earth is basically a vacuum. So it doesn't travel through a medium. It can also travel through air, but that's the thing, like it can travel through a vacuum because this infrared radiation is carried by infrared waves. Infrared waves is a type of electromagnetic wave. Like basically it has a larger wavelength than light waves, if you understand. I mean, it's kind of a light wave but with larger wavelength. Like it has a low frequency wave with larger wavelength. Because if you don't know about waves, it might be a bit harder to understand, but like something like a light wave which carries heat, and that's what we call thermal radiation. So basically power is obviously, like you get the point, energy per unit time. So like whenever thermal radiation is emitted, it's a energy in the form of heat, or this power is also called the luminosity. So this is the power we get, like it's directly proportional to the surface area and the fourth power of the temperature. That's what our law says. So basically it's the amount of energy that is being emitted per unit time. That's what the formula is saying. So I hope you get, like, temperature is obviously showing like how hot or cold something is. That's what's temperature. And surface area means the total area of the surface of a whole body. Like whenever sun emits heat, it's basically a like a sphere. So like the total area of this surface is dependent on the power. I mean, the power is dependent on this total surface area, right? So let's try to solve a problem if you get all the points. So they give us the information. This should be a simple algebraic, like it can be easily solved using algebra. So let's solve it. So here we are given the power and the cross-sectional, then the surface area. So now we need to find the temperature. So let me write down the equation. They said P equals to AT4 times sigma. It's also important to know that the temperature you will get will be in Kelvin. The Kelvin is the SI unit, like it's, and the relation between temperature, the relation between Kelvin and degree Celsius is that Kelvin is 273.15 more than Celsius, because Kelvin cannot be negative. Like 0 Kelvin, like basically the concept of Kelvin is that 0 Kelvin is the lowest temperature possible, and that's the thing. And like the scale is similar to degree Celsius, it's just 273.15 more. That's the difference. I hope you understand. So the power is 0.21. I'm gonna plug it into the equation. And the handwriting may not be very good. I'm writing this in Jamboard. The cross section, the surface area is 4 times 10 to the power minus 4. And they have given the value of sigma at the beginning of the question. You can see that. So T4, using my concept of algebra, I can say it is, if you know algebra, you can easily solve this, and if you don't know that, you have to learn it. I hope all of you know how to solve this kind of equations, because that's the very basic you need to know for these competitions. So t to the power 4 will be 0.21, and I'm gonna have to divide this by 4 times 10 to the power minus 4, and then sigma. You can use a calculator for this. So I'm gonna use the calculator and get this result. So will have 0.21 divided by 4 times 10 to the power minus 4 times sigma. I'm gonna put the value of the sigma in my calculator. It is 5.67 times 10 to the power minus 8. And notice I do not have to change the unit of sigma, because all of these units are in, like the unit is in SI unit. So using my calculator, I get t to the power 4 is 9.26 times 10 to the power 9. Now be careful, the temperature we will get, it will be in Kelvin, and I'm now gonna take the fourth root of it. And that's a very important thing. The temperature we will get will be in the SI unit Kelvin, which I talked about earlier. So fourth root of 9.26 times 10 to the power 9 It's about 310.21 Kelvin. Now notice what the question says. The question wants it in degrees Celsius. So whenever we need to convert Kelvin to degrees Celsius, we need to subtract 273.15. So I will subtract 273.15 using my calculator, and there you go, I get the answer 37.06 degrees Celsius. So this is the first problem solved. It was an easy problem. We didn't have to go deep into the concept. We just used the formulas. Okay. They have given now the sphere of the, now they have given the radius of the sun and the temperature of the sun. Calculate the thermal power radiated by the sun. The surface area of a sphere with radius area is 4 pi r square. Okay, what did they mean by the surface area of a sphere is 4 pi r square? Basically, like, if I want to imagine a football in your head, and like a football means like, if you have the, and if you like wrap it out, right, like, yeah, like if you cut it and then wrap it out, then the area of the flat surface you get is basically the surface area, right? The total area of the surface, that's basically the surface area, and it's 4 pi r square for a sphere, like the total area of the surface. So this is also just an easy problem. We just have to plug in our equations. We just have to make sure everything is in the right unit. So power equals to A T4 sigma. So A is the surface area, which should be 4 pi r square. Okay, now I was talking about the unit. The sun has a radius of 696,340 kilometers. So it's in kilometers, so we need to multiply it by 1000 to get it in meters. And it's very important, we need to make sure our units are in SI units. So it's 4 pi r square, so 4 pi r square. So what will r square be? So first we need to convert it to meters. 696 340. So if I want to convert it to meters, I just multiply it by 10 cube, then I square it times T4. So 5778, it's in Kelvin, so we don't have to worry about it. 5778 to the power of 4 times sigma. They have given its value, you can just plug it in the calculator. So the calculator, I will plug in 4 pi times 696,340 times 10 cube, convert in meters, and then square it times the temperature to the power of 4. So like 5778 to the power of 4 times sigma, and obviously I'm gonna check the value of sigma again. It's 5.67 times 10 to the power 8. That will be 10 to the power minus 8. And the calculator now shows it's 3.85 times 10 to the power 26. And don't forget the unit, this is also very important. The unit is watts, joules per second. 1 and 2 basically just simple mathematical calculations. I didn't really have to go through any physics concepts. Maybe we need to do it, maybe we need to know some ideas of physics for the other questions, but let's continue. Assuming that no energy radiated by the sun is absorbed before reaching the earth, calculate the power received by a solar panel on earth with a surface area. The distance between the earth and the sun is this. You can basically know the radius of the sun. The gravitational energy stored in spherical object of mass m and radius r is 3 gm square by 5r. Right, 3 gm square by 5r, where g is something. Calculate the gravitational energy stored in the sun. Mass of the sun is so. Number 4 is also just a basic mathematical thing. Like you just have to equate the formula. Like you just put it in your calculator and do it. So I need to calculate the gravitational energy stored in the sun. So the gravitational energy stored in the sun is 3 gm square by 5r. So I can now just put that in the calculator. So 3 times g is 6.673 times 10 to the minus 11 times 3g m square. So what is m square? 2 times 10 to the 30. This thing is getting squared. And now we need to divide this thing by 5r. So 5 times r. If you remember, they have given r before. Here is r, see it's 96,340 kilometers. Again, we need to convert it to meters again. So in a calculator, you can put 5 times 6, 96,340 kilometers, and then multiply it by 10 cube. That should do it. And we have our answer, 2.30 times 10 to the 41, and then unit for energy, which will be joules. Let's do number 5. We will come back to number 3 later. It requires a bit of idea from physics. So we're coming back to number 3 later. Let's do number 5 first. It's much simpler. Assuming that the gravitational energy is completed converted into thermal energy and radiated by the sun, estimate the lifetime of sun. Right. So this whole energy they're saying is getting converted to thermal energy. So that would lifetime of sun. If you remember, this is the power generated by the sun, and this is the energy, right? And this thing is this energy is getting converted. So I'm going to use a simple formula. I think you know that the power is energy per unit time, right? So P will be So the energy is power multiplied by time, and in this case T will be the lifespan of the sun. So T equals E by P, right? So the energy is 2.30 times 10 over 41 divided by 3.85 times 10 to the power 26, 3.85 times 10 to the power 26. So now we will get our answer for time. We will just use a calculator. 2.30 times 10 to the power 41 is being divided by 3.85 times 10 to the power of 26. We get something like, so T equals to 5.97 times 10 to the power 14, and the unit will be the SI unit of time, which is seconds. So 5.97 times 10 over 14 seconds. So this is the lifetime of the sun. So we would also like to convert it to years to get a better idea, because let's see how much it is in years. So this much seconds. So in order to, so if I divide it by 60, I will get minutes. If I again divided by 6, if I again divided by 60, I will get hours. Then I divided by 24 to get days, and then I divided by 365.25 to get in years, and that 0.25 is due to leap years. So my answer is what? 18.92 times 10 over 26, 10 over 6 years. So about like, okay, look, just say it's 1.89 times 10 over 7 years. That's how it will be in standard form. 1.89 times 10 over 7 years. So that's like 18.9 million years, and obviously it's quite off from 10 billion years. And they said it's going to differ greatly from the value we estimated. Obviously 18.9 million is like, obviously 18.9 million years, it's far away from 10 billion, and that's not a problem. It's just the math, so you just have to do the math. So 1.89 times 10 over 7 years. Now we will move to the question. I remember doing all of these questions 1, 2, 4, 5 because they are just some mathematical questions, anyone can do it. So basically this is question number, okay, like anyone can do basically 1, 2, 4, 5, yeah, like those are just mathematical questions. Number 3 is where you need a great knowledge of physics, and if you don't have that, that's gonna be a problem. So let me show you, let me give you some concept before solving this problem which will be needed. Let's say this is the sun. So obviously it's radiating heat due to its high temperature, and radiates heat everywhere. Now, if the earth is here, how can we find the heat received by the earth or something? Right, so we need to use the concept of intensity first of all. So, like, whenever anything radiates power, like at every certain point from it, there is an intensity. So, like, if you have a power source and if we go a distance r from it, then at that specific point, like at a distance r from a power source, there is something called intensity. So the power from a formula for intensity is P by 4 pi r squared, and at a distance r from the power source. Now, what does this formula represent? I'm gonna tell you all these things. So I will tell everything. I will tell you what's this. So first of all, intensity is the power per unit area, right? Intensity is the power received per unit area, and this is a very important concept. You will know it later when we are solving the problem. So power per unit area, so like if we have something like this, having a cross-sectional area of A, and it receives a certain amount of power P, the intensity is said to be P by A. So what's this thing P by 4 pi r squared? Now if you remember, 4 pi r squared is a surface area of the sphere, and that's what A is in this case. But why? I'm gonna show you why this is 4 pi r squared. So let's say this is a power source emitting, and we want to find the intensity at this point at a distance r from the power source. So let's say this is our sun, it's emitting heat, and what's the intensity at that point? Like, so you can imagine, like if you are very close to the point, close to the sun, the power received per unit area will be more, and here it will be less. That's why the planets that are closer to the sun are obviously are more hotter. So like Venus and Mercury, they are more hotter than Earth. I mean, Venus is hotter than Mercury. That's because of the atmosphere, if you wonder why. But that's an exception. And if you also think about planets that are further away from Earth, they're obviously colder than Earth. So like, so yeah. So how do we find the power per cross-sectional area from here? So let's say this is a radius r. Now let's do one thing. Let's say the sun is our center, and let's draw a sphere, right? So having sun as our center, we draw a sphere which has a radius of r. Let's just say r is the distance from sun to earth. So now the distance. Now we draw an imaginary sphere of radius r having sun as our center, right? Now at any point of the sphere, now how do you define a sphere? Like, the distance from the center to the surface of the sphere is always fixed, which is the radius of the sphere. So if I go any point of the sphere, it will be always the radius r from the sun, right? Which means if I want to find intensity at any point, like obviously they're all the same distance from sun, so the intensity at all of these points will be the same. So like if I use I equals to P by A, obviously power is the power emitted by the sun, which we have calculated. But what is A here? So A will be the surface area of this whole sphere having the radius r. What is r? The distance from sun to earth. So it's a very huge sphere, and sun is in the center of it, right? And like the intensity is same everywhere on the surface of the sphere. So the area in this case will obviously be the total surface area of the sphere. So it will be 4 pi r squared, and this is how we get the formula. And how will this help solving the problem? Let's get into it. So exactly, when I talked about intensity, this is the first thing. we will use the concept of intensity in this problem. Assuming that no energy radiated by the sun is absorbed and given the distance, and so first of all we will find the intensity at a distance of 1.5 times 11 meters away from the sun, right? So what's the intensity at Earth? So it will be P by 4 pi R squared. So we know what P is. P is 3.85 times 10 to the power 26. So 3.85 times 10 to the power 26 divided by 4 pi R squared. Just gonna write it R squared. I'm just gonna put it in the calculator. So I have 3.85 and the power of intensity will be watts per square meter, right? Watts per square meter, that will be the unit of intensity. So I have 3.85 times 26 as P. I'm going to divide this by 4 pi R square. So what's our R square? So it's 1.5, 4 pi times 1.5 times 10 over 11. This thing will be squared. Right? And this is the intensity out. 1361.66 watts. Watts per square meter. So we found the intensity is like 1361.66. So how does this solve our problem? So we need to find the power absorbed by the solar panel, and it has a cross sectional, it has a surface area of 1.6 square meters. So here's the thing. So intensity is the power per unit area. So similarly, the power absorbed, P absorbed, so the power absorbed will also be the intensity times the area. So intensity is the power per unit area, so power will also be intensity times area. So here area is basically a very small part of this sphere, if you notice. Like this is a huge sphere and here we have a solar panel. So this solar panel will only receive a certain amount of heat, right? Like the total heat is received by this huge sphere, but the solar panel will only receive a very small portion of this heat. That's so here the area will be the solar area of the solar panel. So I have the intensity which is 1361.66 times the area of the solar panel, which is 1.6. So the concept is not very hard, it's just the concept of intensity, and you will be able to solve this, and I hope you got the concept very well, and that's what I'm trying to do here. So I'll just multiply the intensity with 1.6. It's 2178 0.6. 65 watts the power absorbed, so it will be, the unit will be watts. Also don't forget that. And yeah, that's what they asked, the power received at a solar panel, which is also basically the power absorbed, we can also say. And this is the one which needed a bit of knowledge, and I hope you all understand. It's a really interesting problem, and it's also my first video at center of circle as a mentor, and I hope I was able to explain the concepts clearly whenever I use them. And if you have any doubt, leave it in the comment, I think. And this is the end of this video. I hope everyone learned something new. Maybe it could be the amount of radiation or intensity or whatever.